Every minute, over 500 hours of new video are uploaded to global media platforms. To monitor copyright, the system must check every second of that incoming footage against a reference database containing over 100 million active files. Comparing raw video files frame by frame at that scale is computationally impossible. The storage read times alone would cause the ingestion pipeline to grind to a halt. You might assume the solution is to use a standard cryptographic hash, like SHA-256, to quickly check for duplicates. But for media files, standard cryptography fails. Cryptographic hashes are mathematically designed to be brittle. Altering a single pixel or slightly shifting the audio pitch produces a completely different alphanumeric string. The system would register the file as completely unique, entirely missing the copyright infringement. To solve this, engineers need a way to extract perceptual signatures, mathematical representations of the media that remain invariant even if compressed, cropped, or distorted. Tech giants handle this using a distributed architecture known as the Hasher-Matcher-Actioner, or HMA, framework. HMA strictly separates the workflow into three decoupled phases: hardware-accelerated ingestion and decoding, stateless feature extraction, the hasher, and an approximate nearest neighbor search, the matcher. Isolating these components is the only mathematical way to confirm copyright violations in real time, at massive scale, while sustaining a required 99.7% uptime. The architecture begins at the edge. Raw media uploads first hit an API gateway, which acts as the front door for global traffic. To handle unstable mobile connections, this gateway coordinates chunked, resumable file transfers, dropping the raw binary data directly into temporary cloud-based object storage. The moment the data lands, the system performs a quick, exact match check by running a SHA-256 hash of the binary against a high-speed key-value store. If the binary exists, the flowchart hits an early exit, terminating the process. But if the hash is unrecognized, the file is unique. The system routes this asset into an auto-scaling array of Kubernetes worker pods for deeper analysis. Inside these pods, GPU-accelerated hardware decoders rip open the heterogeneous user formats to extract the raw, uncompressed audio and video frames. By filtering out exact duplicates immediately, the ingestion layer conserves those expensive GPU decoding cycles exclusively for entirely new media. With the raw signals extracted, the data moves to the hasher module for stateless feature extraction. Let's look at the audio pipeline first. The system uses classical audio fingerprinting techniques, heavily relying on Wang landmark-based hashing, the core logic that powers Shazam. The algorithm takes the one-dimensional audio wave and applies a Fourier transform to create a two-dimensional spectrogram, mapping frequency over time. The diagram shows a two-dimensional spectrogram. As audio plays, the algorithm scans for high-energy spectral peaks, isolating them as distinct data points called onsets. The system then groups these isolated peaks into pairs, drawing connections across the spectrogram to form a constellation lap of landmarks. These landmark pairs are translated into math. They are parameterized by the frequency of the two anchor peaks and the exact temporal interval, or delta time, between them. Because this method relies on the relationship between peaks rather than the raw audio data, the resulting hash survives ambient noise, heavy lossy compression, and even slight tempo changes. The audio hasher ignores superficial acoustic degradation. It extracts the structural skeleton of the song, distilling complex audio into a clean, searchable signature. The video pipeline has to solve a harder problem. It must capture spatial invariance within a single frame and temporal invariance across a sequence of frames to survive edits like cropping or letterboxing. For this, the industry relies on algorithms like Meta's TMK plus PDQF, the temporal match kernel, and perceptual discrete quantization. We see the spatial hashing process here. First, the algorithm converts the frame to grayscale and downsamples it. Next, it divides the image into a 16 by 16 grid, applying a discrete cosine transform to output a 256-bit binary vector. To account for time, the TMK algorithm steps in. It takes these frame descriptors and averages them over periods of sine and cosine functions, securely encoding the sequence's temporal signature. This syntactic hashing is fast, but it can be fooled by semantic modifications, like a user recording a television screen with their smartphone. Detecting low confidence, the system falls back on deep vision transformers, like RFDETR, to extract heavy object-aware features that truly understand scene context. By cascading from computationally cheap spatial transforms up to complex semantic models, the pipeline creates a tiered defense that makes evading detection mathematically unfeasible. Those generated 256-bit hashes are then sent to the matcher phase. Here, the query vector must be compared against the 100 million item reference database. Running an exact brute force distance calculation against every file in the database has an O of n time complexity. At enterprise scale, the latency makes this impossible. The solution is an approximate nearest neighbor, or ANN, search architecture. This requires dedicated vector databases, like Milvus or FACE. These databases typically use a baseline index structure known as inverted file with product quantization, or IVPQ. Looking at the inverted file layer, the database clusters millions of vectors into distinct polygonal regions called Voronoi cells. When a query arrives, the system only searches the single cell it lands inside, instantly pruning the search space. Inside that cell, the product quantization layer splits the query vector into smaller subvectors, matching them against a reference codebook. This compresses the memory footprint by a factor of 16. However, a stacked hardware bottleneck remains. The CPU is forced to frequently read the quantized lookup table from system RAM, which slows down the search. To bypass this memory bottleneck, engineers implement Google's scan index optimization, which utilizes a technique called FastScan. Scan takes the typical floating point distance measurements and aggressively compresses them into tightly packed 4-bit integers. This enables a precise physical hardware manipulation. Scan packs 32 of these 4-bit vectors into a single 128-bit CPU register. It transforms thousands of slow memory reads into one incredibly fast SIMD shuffle instruction, executed entirely within the processor. By packing data directly into the CPU registers, Scan pushes the physical limits of the silicon, executing billion-scale vector retrieval in less than a millisecond. When we step back, the complete hasher-matcher-actioner architecture comes into focus. This schematic shows how the distinct modules govern the entire pipeline. This strict separation of concerns is what allows the platform to scale horizontally under heavy load without crashing. We can trace a single upload's lifecycle. It enters through the Envoy proxy, clears the GPU decoders, and is processed by the stateless PDQ or landmark hashing nodes. The resulting perceptual vector then flows into the scan-optimized vector database for sub-millisecond similarity matching. If a match is detected, the database pings the final component, the actioner. This module executes the specific business logic required, whether that means monetizing the video, flagging it for review, or issuing a strict takedown. The actioner logs these state changes into a highly consistent, globally distributed transactional database, like Google Spanner, securing the data lineage and licensing history. Modern copyright enforcement at this scale relies on marrying classical digital signal processing with highly optimized register-level database architectures to govern global media flows.